So this is the thing that is happening in the marine heat wave, that the surface becomes so warm, it becomes so light that it cannot sink. So it cannot sink means it cannot transport the heat from the surface layer to the bottom of the ocean, or like to the deeper layers. So it is always staying there, keeps warming up. That tropical cyclone, especially in the Bay of Bengal, is like rapidly intensified within less than 17 hours, and and not only rapidly intensified, it turned into a super cyclone. Yep.
Hello, everyone. Welcome to Climate Converse podcast. It's a podcast channel where we talk about the world as it is and the world as it could be. And today we have a very special guest, Dr. Saurabh Rathore. He is an assistant professor at IIT Delhi and he's also a climate scientist. I have known him for over a decade and we have come a long way together. So, Saurabh, a warm welcome to the podcast.
Yeah. Thank you, Mainak.
So, Saurabh, I want to start the discussion by asking about your academic journey, where you started and how you end up as an assistant professor in climate science.
Sure. So my schooling happened at my hometown, that is in Rajasthan, Ajmer district. And for my engineering, I went to Pune, where I did my aerospace engineering. And after that, I cracked GATE exam, and then I moved to IIT Kharagpur for my MTech. So I wanted to get the aerospace branch or the mechanical branch or the cryogenic branch. So this thing was my last option in my gate choices, and I
Okay.
and and I end up here in my last option.
So, do you reckon you being a climate scientist is a random event, a stochastic process?
You can say that, because I was having an offer from IIT Madras in ocean engineering department for hydrodynamics.
Okay.
And then I was having one more offer from like DIAT. I have given the interview of the Defense Institute of Advanced Technology, DRDO, in Pune. So I
Mhm.
was also waiting for the outcome of that. So I don't know what had happened with the DIAT, but I got an offer from IIT Madras for hydrodynamics in ocean engineering, but it was an MS.
Okay.
So, and then I got an offer in IIT Kharagpur MTech. So I don't know like what had happened. I thought that okay, MS is for 3 year and MTech is for 2 years. So let's go for a 2 year course rather than going for a 3 year course. So that's how I went to IIT Kharagpur for my MTech.
And what
And then
happened after that?
yeah, and then after that, what happened, like for the first 6 months, I was not able to understand what is Coriolis force, because I have never studied this force. One day, Professor Mandal, he wrote the name of this force on the board. So
Mhm.
I and my friend, we were so surprised. Oh, this is the force that he always talks about. That is after a semester. Okay, so after that, like I have applied for my PhD in 2015. So what
Okay.
happened, like I was having a choices of like three projects of the PhD.
Mhm.
So I selected a project about water mass changes, circulation changes, and
Mhm.
the hydrological cycle changes. So what happened, like my application was on hold on that round.
Okay.
So in that thing, I joined IIT Kharagpur as a PhD. Okay, after my MTech. So I was just waiting for the outcome, and like my application was on hold because of some funding issue or something in Australia. One day, Professor Nathan Bindoff, he just emailed me that, "Are you still interested in doing the PhD here in Australia?" I said that if it is the same project, that I will do, otherwise I have to think. So I was
Mhm.
having no clue who is Professor Bindoff, and like why he's emailing me after one
Nathan
year.
Bindoff, for
Nathan
the
Bindoff.
viewers, he's a big shot. He's a big
Yeah.
shot in this field.
Yeah, so I was having no clue who is Professor Nathan Bindoff and like why he's emailing me after 1 year.
Mhm,
So I just threw a question to him that if it is the same project that I applied for that I'm interested, so I will take that project. Otherwise, I have to think. So at the time of my application to for PhD in Australia, I received two offers, one from Matt King and one from Helen Phillips.
mhm,
So primarily that project was having a PI of having Helen Phillips as a PI, which eventually like taken by Nathan Bindoff as a PI and Helen as a co-PI.
mhm,
When I was applying for the PhD, I received an offer from Matt King, and it is about the basal melting of Antarctic ice shelf. So
mhm,
from the tidal effect. Okay. So
mhm,
so this was the project that Matt King offered me, and then he said, I'm happy to take you as a PhD. On the same day, I got the confirmation from Helen Phillips about the circulation changes, water mass changes, okay, and ocean heat content project. So I was so tense, like how, because they both are from the same department. So how, after accepting the offer from Matt King, how I can say no to him? So I was so tensed. So I just emailed Helen Phillips that, see, I got an offer from Matt King, but I'm more aligned to your project rather than Matt King's project. So I don't know like what to reply and like what to tell to Matt King about this thing. Will he feel bad? So Helen said that this is absolutely not a problem. It's your PhD. You should look for your interest, and Matt King will not and will be okay. He won't feel bad for anything. So what happened? Like I just sent an email to Matt King, explained him all the situation, and Matt King was so chill, so cool. He said, "That's all right. Okay, Saurabh, you can just take that project where your interest aligns. So
mhm,
don't worry about this project." So that was a very good experience for me, that how, like, without taking into the any sort of like tense condition, he just said, that's fine, you can take Helen Phillips project. So I went with Helen Phillips project and I got that offer after 1 year. Then I joined. Okay. So so my first interaction was with Nathan Bindoff was like, I went to his office and I saw that Nobel Peace Prize copy is there. Okay, and I was so shocked that after having a meeting with Nathan, I came to my desk, I opened my laptop, and I searched about him, that who is Nathan. And I said, my God, he is a very good, very big shot.
yeah, yeah.
Yeah. So he
So
received Nobel
quite a
Peace
journey.
Prize.
So let me ask you again, what actually sparked your journey into Indian Ocean research? So because you um, like you started from a different background, and then
Yeah.
you ended up working on ocean heat wave, right?
Yeah. 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 So, so it is always about. I can't say that my research is limited with the Indian Ocean sort of thing, because I love to do the global stuff, and I am so much fascinated about the Southern Ocean dynamics and the role of Southern Ocean that will into the role of Southern Ocean into the anthropogenic heat uptake and the carbon uptake and like that sort of thing. So but Indian Ocean is a part of my research where I love to do the extreme heat, extreme warming of the Indian Ocean that we call as a marine heat wave. So after submitting my thesis, I noticed one thing, that okay, there was a super cyclone Amphan. Okay, during that
Okay,
period.
okay. We'll come to that, but
Ah, okay, yeah.
let's first linger on what is
Hmm.
marine heat wave for our viewers who
Yeah.
probably doesn't know much about it.
Yeah, okay. So marine heat wave is I want to explain it in a very layman language so that everyone
Yes.
can understand. So marine heat wave is the extreme warming condition. It's like a discrete event that happen at the ocean surface or in the subsurface also, where the temperature rise up to like a very high conditions, and it gives the extreme warming condition, okay,
Mm,
of the ocean temperature. So that's why we call it a marine heat wave. So you can link it with the atmospheric heat wave. That's we call as Lu in Rajasthan. That
Mm-hmm.
it is a heat wave condition that the very warm winds are blowing over the land, and then we can feel it during the daytime of the summer. So it is the same sort of phenomena that happens over the ocean, that is a these are extreme temperature conditions that develop somewhere, and then it covers the basin. It covers the basin. So it's very dangerous condition because it is having too much of drastic consequences later on. But this is the extreme sort of temperature conditions that develops over the ocean. The analogously you can have it in the atmosphere also. That causes atmospheric heat wave.
So let me be devil's advocate,
Mm,
pretending that for our viewers who doesn't know much about it, usually when one part of any fluid is heated, it
mm,
creates some kind of motion, convective
mm,
motion mostly.
mm,
But when there is convection, the heat gets transported easily.
mm,
Keeping that in mind, if you could explain, how does this kind of heat wave sustain, and
mm.
how, I mean, what is the dynamical or process? I mean, what process leads to marine heat wave?
Yeah. So it's a very good question that why ocean sustains that much amount of heat, right?
Mhm,
Uh, so atmosphere and ocean, first of all, they both are fluid. Okay, they both can flow easily, right? The key difference between the atmosphere and ocean is the density. Atmosphere is like thousand times less denser than the ocean. Ocean having a density of like, let's say, 1,000 kilogram per meter cube, and atmosphere is having a density of 1.23 kilogram per meter cube, something like that, right? But it's like thousand times more denser. The ocean is thousand times more denser. So because of it, the heat capacity of the ocean is so high. It's like
mhm.
4,000 joules per kg Kelvin as compared to the atmosphere. So oceans or the waters take a lot of time to get warm up, a lot of time to get cooled down. Okay, so the inertia, the thermal inertia of the ocean is very high. So once the ocean started warming up, it takes time to get warm. But once it get warm, it can retain that heat for like a several days or weeks also. So I'm just talking about this marine heat wave context. But if you go for like the total amount of heat stored into the ocean because of the climate change is insane. It's like you can say thousands of atomic bombs amount of heat is stored into the first couple of layers in the ocean. So and
So,
that
first couple of layers in meters, how much would be in general?
oh if we talk about for the first 700 meters of the ocean, first 700 meters of the ocean, the every decade the ocean, the first 700 meter of the ocean, every decade is storing a heat of 20 into 10 is to power 21 joules per meter square.
So it's in petajoule. Something.
Yeah, yeah, it's like zeta joules or like
Okay.
zeta. Beta is 15, zeta is I think 21 or 22. Yeah. So like this much amount of heat is stored by every year or every decade by the ocean in the first couple of meters. So that amount of energy is insane. Okay, it is the rate of the heat accumulated every decade.
Mhm.
So, so the marine heat wave, so we call it the ocean heat content, but marine heat wave is the instantaneous warming of the ocean surface. Like it occurs at the I'm not going to go into like the deeper part of that thing, but the marine heat wave is occurring on the surface, let's say. So it takes time for the marine heat wave to dissipate. So
Mhm.
once the marine heat wave develops over the ocean surface, it may be for a couple of days or couple of week, or maybe a prolonged marine heat wave is also there that may exist for 180 days or like 9 months or so. It's very easy.
Mhm.
Yeah. So and then ocean needs a phenomena to disrupt this event. So the
Mhm.
in terms of the dynamics, the advection plays a very critical role, that bringing the heat from one place and then going and then transporting it to the other place so that it can covers the entire basin. And while it was covering the basin, it expands its area also. So it generates at one point, then it travel with the help of advective behavior of the ocean, and then while traveling, it receives extra amount of energy, so it covers, it is spread the whole basin. So this is
Mhm.
the dynamics related to the, but there are other dynamical factor as well, but it depends like what dynamical factor is responsible for what sort of marine heat wave typically. But advection plays a lot of critical role into it. And other than the advection, the heat fluxes that the flux, the heat exchange between the ocean and atmosphere at the surface layer, it is also playing a very crucial role to developing and to sustaining the marine heat wave. So suppose if there's a marine heat wave over the ocean surface, but the atmosphere is so cold, so it can
Mhm.
kill the marine heat wave.
Okay.
But the atmosphere is also warm.
Mhm.
Suppose the ocean is cool, but the atmosphere is so warm, so it can generate a marine heat wave also because of the heat exchange between the ocean and atmosphere. That's called surface heat flux exchange. So heat
Mhm.
fluxes and advection play a lot critical role for developing and sustaining the marine heat wave.
So in world ocean, are there some hotspots where you often get to see those marine heat waves?
Oh yes. The Pacific, the Eastern Pacific Ocean, the North Pacific Ocean, that we call it like a blob, the blob. So the blob is a phenomena that occurs, I think, in the Pacific Ocean in the subsurface. So it just appear as a like a warmer subsurface, and then it sustains there, and then it disappear. So people call it the blob. I think if I'm not wrong, it's in Pacific. Then the Tasman Sea, that is below the Australia. There is a sea that surrounds the Tasmania. It's called Tasman Sea. Tasman Sea is a very prominent hotspot for the marine heat wave. Then Bay of Bengal is also the hotspot of the marine heat wave per se. Yeah.
Mm.
So so there are these hotspots are very regional, but they are spreaded across the globe depending on the intensity of the marine heat wave and how frequently they are happening there.
So I understand one thing. When you warm any fluid, it it tries to stratify. So the lighter fluid goes on top and the heavier fluid goes at the bottom. So does it help the marine heat wave in any way? Because if the lighter water gets to the top and it keeps warming, heat can accumulate, right?
Yeah. It's a it's a very very relevant question for this context because the stratification is acting as a brick layer, is a layer of brick that won't allow the surface property to get mixed with the deeper depths, right?
If you could explain in a more like non-technical way.
Okay. Yeah. Okay. Sorry. Yeah. So there's a phenomenon called stratification. Okay. So how stratification develops? Let's first understand this thing. So suppose you are having like these are the three layers of the ocean. So this is the top layer, middle layer, and bottom layer.
Mhm.
Let's suppose. Okay. So there's a lot of sunlight that is coming over the ocean surface. Okay. So when the ocean surface gets a lot of heat, it becomes warmer. Okay, so the winds blowing over the ocean surface will become slow down. So now the winds cannot evaporate the water from the ocean surface. So if the water will not evaporate from the ocean surface, so the surface will not become cooler. So it become warmer and warmer because the winds speed slow down as the ocean surface gets warmer. Right? Now this warmer the
If
surface.
you could explain a bit, like why would the wind get slowed down on a warmer surface?
Yeah, it's a it's like a chicken and egg problem because it's hard to say that what is causing what. Are the slower wind hitting the surface, or hitting the surface making the wind slow?
Okay.
So the exact process is like a chicken and egg problem because usually winds blow from like high pressure to low pressure.
Yeah.
Okay, and if there is a high pressure, the surface should be cool, and if there's a low pressure, the surface should be warm because a warmer surface creates a low pressure sort of
Mm.
condition, and a cooler surface creates a high pressure condition. So it's the winds always blow because of the pressure difference, Okay.
So our viewer can ask, like, when you read in the newspaper or like in the news, there is a low pressure system.
Mm,
Presumably, there would be storms and
mm,
like lot of winds over a low pressure system.
mm,
So, if wind blows, then it
mm.
can carry the heat away, right?
Yes,
So,
yes.
does it mean that the the heat in the ocean or the like
Mm,
marine heat waves
mm.
is over the region where there are not much flows going on, or if there are like high pressure zone? Is it always the case?
No, actually, in marine heat wave, why marine heat wave is created? So I'm just talking about with respect to the winds. So when the winds are blowing over the ocean surface, it helps the water to evaporate. So water is changing its state from water to a vapor state. Okay,
Mhm,
there's a lot of latent heat flux loss. Because the water is changing its state from the water to vapor because with the help of the wind. So the ocean has to lose the heat to the atmosphere in terms of the evaporation process.
mhm.
Okay, and this heat loss is the latent heat loss.
Okay.
Okay, so because of the latent heat loss, the ocean surface becomes cooled down. Now, suppose if the winds are slowing down over the ocean surface, so it is not prompting the ocean surface to lose the to lose the latent heat. So to it is not helping the ocean to evaporate the water. So when the
Mhm,
water is not evaporating, the ocean surface will keeps on warming, 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 and then it will develop a marine heat wave. So this is from the perspective of the winds, right?
mhm,
But you ask about that, what happened to these layers now? So if
mhm,
the evaporation is not there, so the top layer is become warmer, warmer, warmer. So warmer the surface is less denser. Cooler the surface is more denser, right?
mhm,
So if there are three layers, if this surface is warm, it is not having enough ability to mix or to go down because this is warmer. Warmer the surface is lighter the surface. Okay, cooler the surface or like cooler the fluid is denser. Cooler fluids are denser, warmer fluids are lighter. Okay, so this is the lighter layer that always stays at the top. It is having no ability to mix and to go into the deeper depths of the ocean. But once the layer become cooled down, it become dense and it sinks. It goes into the bottom of the ocean. So this is the thing that is happening in the marine heat wave, that the surface becomes so warm, it becomes so light that it cannot sink. So it cannot sink means it cannot transport the heat from the surface layer to the bottom of the ocean or like to the deeper layers. So it is always staying there, keeps warming up. So this process is known as stratification. When your ocean become this layer become so much lighter that is they are unable to mix with the deeper layers of the ocean. So
mhm.
they are unable to mix the heat or to transport the heat to the deeper depths.
Okay.
So this phenomenon is known as stratification. So this stratification will act as a brick wall. Like it is hard to break this wall to put the heat into the deeper depths of the ocean. It is nearly virtually impossible to break that stratification. Okay, so the heat will get trapped into this upper layer of the ocean and it become warmer, warmer, warmer and lighter, lighter, lighter. So it is unable to mix. So this is called
Mhm.
stratification. Now this stratification is one of the key reason for the development of the marine heat wave because this layer become receiving the heat from the sunlight and keeps on warming up and it develops a marine heat wave at some point of time.
So let's now talk about what are the implications of marine heat wave. I think one of your highly cited paper where you worked on the super cyclone Amphan and the presence of marine heat wave. If you could
Hmm.
elaborate more on that.
Yeah, so I started working on that paper independently after submitting my thesis with two of my other friends, you can say. So one is Mayank Mishra from IIT Kharagpur and one is Babita Jangir. So Babita is a postdoc in Israel at the moment. So we three started working on this thing because I was so fascinated by one thing uh, that there was something very strange about this super cyclone that it got like rapidly intensified within less than 17 hours. So this was highly unusual that tropical cyclone, especially in the Bay of Bengal, is like rapidly intensified within less than 17 hours, and and not only rapidly intensified, it turned into a super cyclone. So
Mm-hmm.
that was like really strange thing. And one other particular thing about this super cyclone Amphan was it happened during the spring season, that is March, April, May season, we know as the spring season. So it is the first cyclone ever recorded in this season as a super cyclone. So there are like many strange things that happened with this cyclone. So I was just checking that what had happened at that time. So we did an analysis where we have just plotted the temperature conditions during those time period, and that temperature condition was so high. Like there was like extreme temperature conditions presence over there. So the temperature condition over like, or like I can say beneath the cyclonic track was higher than 2 degrees Celsius than the average temperature. So like 2 degrees Celsius more temperature was there, like above average. 2 degree more some
So,
more
what
temperature.
is the general average temperature over Bay of Bengal?
Yeah, so the average temperature of the Bay of Bengal is almost stays around like 28 degrees Celsius, 20, like between 26 to 28 on the average. Okay, but this was crossing 30 degrees Celsius actually. So
Mm-hmm.
it was like 2 degrees Celsius above the average temperature. Okay, um, so then we started to investigate that was there a marine heat wave or not. Okay, so then we did the analysis and we found out that there was a presence of marine heat wave just beneath the cyclone track, and that marine heat wave fueled the cyclone because when the cyclone is there, okay, when the cyclone
Mm-hmm.
forms over the ocean, and the ocean, and suddenly that cyclone interact with the like a warmer ocean surface or the warmer surface temperature of the ocean, it becomes intensive, it gains the energy from the ocean. Okay,
Okay.
because ocean is the sole source of energy for the cyclone. So as much as the cyclone receive the energy from the ocean, it sustain and become intensify and becomes devastated and deadly also. Okay, so
Is
the
it
ocean is
fair to say, like, when you have a marine heat wave, it would create more water vapor because of, or it is easier to form uh, water vapor, and that cyclone can take up because of the heat wave?
uh, No, so there are two different phenomena that happen here. So first of all, uh, when there is a marine heat wave, okay, so as I mentioned earlier, when there is a marine heat wave, so the latent heat lost by the ocean should be suppressed.
Mm.
If there is a latent heat loss, there is a evaporation, and evaporation will cool down the surface, so it will kill the marine heat wave. So to have the marine heat wave, the latent heat flux lost by the ocean or the evaporation of water from the
Mhm.
ocean surface should be suppressed. Then only there is a formation of marine heat wave. But cyclone is not the tropical cyclone formation does not depend only on the ocean. It needs a conducive atmosphere also.
Mhm.
Okay, so the amount of humidity it requires, the amount of circulation of air it requires, the atmospheric stability is required, so that there
Mhm.
should be no unstable structure. So because tropical cyclone is a phenomena of ocean and atmosphere interaction. It's not only about ocean. It's not only about atmosphere. So both things should work out together to develop a
Mhm.
tropical cyclone. Okay, so in the case of Amphan, what happened that a tropical cyclone has developed. A tropical cyclone has developed. Okay, and then when it was traveling, it got interacted with the marine heat wave, and suddenly it got fueled up into a super cyclone. So this was happened with the Amphan, but in the same season, in the previous year, in 2019, there was one more cyclone called Fani cyclone. Okay, the strange case between Amphan and Fani was Amphan was a short-lived cyclone. Amphan was just there for like 5 to 6 days. On the sixth day, it hit the coast of India. So technically,
Mhm.
it just sustained a 5 day of life cycle over the ocean. Okay, but was a super cyclone. But Fani What happened with Fani? Fani traveled for almost 8 to 9 days over the ocean surface, and then it hit the coastline of India. So, despite of having more lifespan over the ocean, Fani was unable to develop itself into a super cyclone. The maximum stage where the Fani reached was the extremely severe cyclone, not the super cyclone. After extremely severe cyclone, the next stage is the super cyclone. So Fani, even after having a lot of lifespan over the ocean, it was unable to convert into the super cyclone. But Amphan did. The only difference between these two cyclones was the presence of marine heat wave. And the other thing, the atmospheric column was not supportive for the Amphan cyclone. It was very, very unstable that time. But in case of
Mhm.
Fani cyclone, the atmosphere was very, very supportive for the tropical cyclone. But despite of that, Amphan managed to become a tropical cyclone because of the marine heat wave,
Okay.
extreme warming condition.
So let's talk about now what are the other implications of marine heat wave. Regardless, it can severely impact the marine life, right? Um, for the all the species, the
Yes,
marine species.
yeah, yeah,
If you can elaborate on that,
yes, yeah,
what would be? I'm asking you a very bird's eye perspective,
mm,
because as we all know, because of global warming, events
mhm,
like marine heat wave would be more frequent in the near future. So,
yeah.
as an expert, what is your opinion on this occurrence of marine heat wave and the consequences?
Yeah. One of my student is doing an analysis where we have seen that okay, what is happening with the cold spell also in comparison with the marine heat wave. So what we are finding that the cold spell are going down and the marine heat waves are increasing. So marine cold spell
Okay,
they are the opposite.
I need to stop you there. If you could explain in layman terms.
Yeah. So the marine cold spell is the opposite of the marine heat wave, where the ocean surface cools down. So marine heat wave warms the ocean surface, marine cold spell cools the ocean surface. So marine cold spell are going down and the marine heat wave are increasing since
Mhm,
1982 for the Indian Ocean. Okay.
mhm,
Now, in case of marine heat wave, what happens like because marine heat wave forms because of stratification. A lot of heat get trapped into this stratified layer. Okay.
mhm,
So it does two things. First thing, it warms the layer. Okay. So this warming of the layer, what will happen that the marine, we all have some temperature sensitivity. Okay, so I am comfortable for let's say 35 degrees Celsius temperature or 40 degrees
mhm,
Celsius temperature. But a person in Ladakh or the person in UK is not capable to have that much amount of exposure to the heat. So we all have our sensitivity. If there's a lot of heat, we may die, right? So it is the same sort of thing happen with the marine organism. So marine
mhm,
organism, marine microbes and all, okay, marine life like fish and all. So if a lot of heat get trapped into this layer, the fish may die because the fish is not surviving that amount of temperature. So it may die. The marine
mhm,
microbes, marine organism may die because each of them they have a like a temperature threshold. If the temperature rise above that, they die, right? So, so that is why the marine heatwave is creating a lot of fish mortality across the globe. Like, so the Tasman marine heatwave did a lot of fish mortality in the Tasman Sea, and lots of dead fish washed away over the Tasman Sea. Then the Great Barrier Reef in the Australia, right? So it's known as the coral bleaching. Coral bleaching. So corals are always like full of colors and all. Okay, they are having like a very beautiful colors in the corals. Okay, so corals are like
mhm,
the plants present into the ocean, the vegetation presents into the ocean. They are very beautiful if you see. But because of the high temperature, what happened that this coral died because these plants cannot survive that amount of temperature. Okay, and these are like a widespread coral bleaching happen. Okay, and how we identified that they lost their color, so they are dead now. Okay, so this coral bleaching is the widespread coral bleaching is also considered as like a tipping point of our climate change. So tipping point means it is one of the indication that our climate is reaching to a level where the irreversible changes are happening. That once the changes happen, it is hard to reverse it back. Okay, so the coral bleaching is one of the indication of the tipping point of the climate change. And then so these are the fish mortality, coral bleaching. Now what happened that this layer contains the top layer of the ocean contains like a nutrients that are required by the microorganism, the micronutrients that are required by the microorganism. So these micronutrients are like, let's say, like sulfur or nitrogen or iron or silicate, phosphate. So these are the micro nutrients that are present in the top layer of the ocean. So that has been eaten up by the microorganism, and then these microorganisms are eaten up by like a big species, let's say the prawns and krills and all, and then these are eaten up by the fish, and then the fish has been eaten up by like the bigger species like whale and shark and all. Okay, so that this is a sort of like a simplistic chain that we can understand. So it started from the microorganism. Now what happened? The deeper layer of the ocean contains a lot of nutrients, but it requires some mechanism so that this nutrient should come up. Okay,
mhm,
now the ocean layer has become so much stratified, it is unable to mix. It is unable to bring these micronutrients to the top layer where the fish or where the microorganism can eat, and the fish can eat that microorganism. Okay, so so what happened that there is a certain amount of nutrient present, but this layer is stratified. Okay, so micronutrients was consumed by the microorganisms, and then there will be the
mhm,
unavailability of the micronutrients.
mhm,
Okay, so the microorganism will die out of it. So the fish will not come there to eat those microorganisms. Okay, so there is a like a you can say there is a like a less fish available to catch.
mhm,
So am I clear like that what happens here? So the microorganism eats the available macronutrients, and then there is no more macronutrients available there. So the microorganism die. Now the fish who's supposed to eat those microorganisms will not come because there is not enough microorganisms are available. Okay, so that region of the ocean where we will not find any fish. So
mhm,
if we want to have the fish, if so, how we predict that? Okay, how we give this information to the fishermen that okay, go there and catch the fish. There's a high chances of catching a fish over there because we track that the amount of microorganism presence there. There's a lot of microorganism present at particular location in the ocean, so there's a high chance that the fishes will also be there to eat those microorganisms. So the fisherman gives this. So we gave this information. We give this information to the fisherman. Fisherman goes to that particular location and catch the fish. Now, if the macronutrients are not present into the water, so microorganism will not be there. So fish will not come at that location. So fish will migrate to some other location. Okay. So there are like devastating consequences, and it will also lead to the shortage of the marine food, like because India is surrounded by like a very vast coastline, like a lot of population, Indian population depends on the seafood. So it is
mhm,
hard. So it will become difficult for the fishermen to catch the fish if this sort of condition persists for longer period of time. So we are having coral bleaching, we are having fish mortality, the unavailability of the fish there, and the ocean will deplete or will deprive of oxygen content also, because it
mhm,
requires mixing for the ocean to catch the oxygen from the atmosphere and then supply it to the ocean. Okay, but if this stratification will happen, it is unable to mix. It will unable to catch the oxygen from the atmosphere and then supply it to the ocean because of this stratification. So these are anoxia condition, or like I say, it's hypoxia condition or something like that. Okay, where there is a less availability of the oxygen in the ocean water. So
mhm.
these are the consequences that we may face with the increasing marine heat waves.
So we are almost at the end of our conversation. So I don't know if there is like we can end in a positive note because we all know how it is going. But in
Yes.
spite of that, I would ask you, how would you uh, like to tell our viewers how to cope with the changing climate and marine heat wave?
It's a very, very difficult question to answer uh, because the problem with ocean is are like once the changes started in the ocean, it is become irreversible. Like we cannot reverse the things for the ocean because the inertia of the ocean is very, very high to. First, it is very difficult to change the ocean, the things in the ocean. But once that has started to change, it is almost become impossible to reverse it. It takes decades or century or millennia for the ocean to stabilize. So, for example, suppose if all the countries today decided that okay, let's not emit the fossil fuel or let's not put the carbon dioxide into the atmosphere from today, right? Okay, so whatever be the carbon dioxide that was emitted till yesterday,
Mhm.
that will stays in the atmosphere for like couple of decades or maybe for a century. So the amount of global warming that will be created by the CO2, that will ultimately end up into the ocean. So ocean will take up all the heats because of high heat capacity of the ocean. So ocean started to warming up, and when the ocean started to warm up, the sea level rise will happen. Okay, and it will be a continuous process, and we don't know where this sea level will be stabilized in the future and in how many years it will stabilize. It is very hard to say that where the sea level will become stabilized or stop increasing. It may take couple of century, it may take a millennia. We don't
Mhm.
know. So this is the consequences that the changes in the oceans are irreversible and beyond the human life scale. Okay, we don't know where the ocean will become stabilized. So if this sort of phenomena have started occurring into the ocean, like let's say marine heat wave or something like that, okay, they will be growing for sure in the future. Okay, the only thing that can prevent it happening or like that can slow down these sort of frequencies of these events is to limit or eliminate the fossil fuel burning, like just to cut ourselves not to put extra carbon dioxide into the atmosphere. So it's just related with the fossil fuel burning. So if you put a lot of CO2 in the atmosphere, this sort of phenomena will grow and like will increase in the future. That's it. So um, uh, like you asked, like where we are heading into the future. So the future is about we have to restrict ourselves not to cross 1.5 degrees Celsius above the pre-industrial level. So what is 1.5 degrees Celsius? It is the globally average surface air temperature above the pre-industrial levels of temperature. So that is from 1850 to 1852, I think 1900 or something like that, or 1920. So whatever be the temperature between 1852 to 1920, year 1920, okay. So we should not go, or we should not cross 1.5 degrees Celsius of the average temperature of this area, of this era actually.
Mhm.
So we are more worried about are we crossing the 1.5 degrees Celsius mark of the global surface air temperature. So it got hit twice in the last 3 years. It got hit twice the 1.5 degrees Celsius mark, and then it came down. Okay. So I don't know what will happen in the future. Are we actually like intended to cross it or not? Okay. So if you look the current state of the ocean. So someone has posted on the LinkedIn about the current sea surface temperature, and there are a lot of heat waves across the globe. Lot of heat waves across the globe. So the sea surface temperature of the globe is already very high.
Mhm.
If once we cross this 1.5 degrees Celsius, okay, so we are tipping our climate to a new state. We are heading towards a new state of our climate or new warmer state of our climate. And then if we hit the 2 degree Celsius mark, it's all devastated. We are mark from the IPCC is the key indicator that we should not cross it. But the current state of the sea surface temperature across the globe is like very very high, very very high. So these are the like takeaways that we have to limit our the greenhouse gas emissions, especially the fossil fuel burning.
Thank you so much, Saurabh, for this wonderful discussion. And thanks to our viewer. And we will see you in another episode.